Group B, and I will be presenting for the part A for the linear diet. And this is my group member. And our topic is linear diet and its practical application. Okay, so what is linear diet? A linear diet is a silicon PN junction that is designed for operation in reverse breakdown region. A linear diet breakdown characteristics are determined by the doping process. So when a diode reaches reverse breakdown, the voltage remains constant even though the current changes, and this is the key to the linear diode operation. This linear breakdown characteristic, so this is the diagram. As the VR increases, which is this one is VR, so the reverse current, which is IR, this one, will remain extremely small up to the end of the curve, which is the curve. So the reverse current is also called linear diode, which is the inside. Vs is also known as I. So at the main point, the breakdown line begins, which is at this point. So the internal linear resistance, which is like that, begins to decrease. So it will decrease. The reverse current also increases rapidly. So the linear breakdown, which is Z, voltage remains nearly constant with voltage breakdown of 1.8 to 200 volt. This is the diagram for linear regulation. Linear regulation has the ability to keep the reverse voltage constant across its terminal. Is the key feature of the linear diode, and it maintains constant voltage over a range of reverse current values. The minimum reverse current, which is IZK, this one, must be maintained in order to keep diode in regulation mode. So voltage decreases drastically at this point if the current is reduced below any of the curve. So above IZK is this one. Maximum current is linear major damage permanently. The next is linear diode application, which is linear diode as a voltage regulation. The linear diode is used as a shunt voltage regulator for regulating voltage across small loads. So this is the DC input voltage from rectifier or smoother to circuit. And this is the V in, and this diode here, and this is the V out. This is linear diode's application. This is linear diode in phasing circuit. As we see in this diagram, this is the input waveform, and we have two diodes in the middle. So the output will be like this, because the linear diode is used for modifying AC waveform, keeping circuits by limiting the part of AD1 or both the half cycle of an AC waveform. So these two diodes will clipping circuits and limit the part whether the half or both cycle of the waveform, and the output will be like this. So next is linear diode application, which is linear diode involved voltage protection. So when the input voltage is higher than linear breakage voltage, the voltage across the resistor drops, resulting in a short circuit. This can be avoided by using the linear diode. So this is the diagram. So when it without a linear diode, the voltage will be over. Voltage occurs when it turns on. As you see, the diagram is up to the peak. And when it reaches linear diode, the linear diode will absorb the over voltage, so the peak will be flat like this, and the voltage will be 20.
Continue the presentation with part B1, which is N-channel of bipolar junction transistor and field effect transistor. Transistor selection. We selected the 2N2222 NPN BJT for this project. This is one of the most widely used transistor in electronic education and prototyping. Its popularity comes from its well-understood characteristic, making it ideal for learning and analysis. It's frequently used in amplifiers, switches, and signal processing. It's suitable for small signal application. It also features a high current gain, beta, meaning a small base current can control a much larger collector current. This is important in amplifying circuit. In this slide, we show the 2N222 datasheet highlight. Here are some key parameters for this datasheet. Collector emitter voltage is 40 volt. Collector current is 600 milliampere. Total power dissipation is 625 milliwatt. And the DC current gain ranges from 100 to 300. Meanwhile, the saturation voltage is 0.37 at 150 milliampere collector current. This specification shows the 2N222 can handle moderate power levels and is reliable for various basic applications. Next is F transistor selection, which is the FET selection. For the field effect transistor, we selected the 2N3823 N-channel GFET. We choose this because it is a standard component used in both analog and digital electronics. It operates in enhancement mode, which make biasing easier. It is ideal for low power switching application. It supports fast switching, which is useful in PWM control, logic circuit, and a load management. Next, I will show you the 2N3823 datasheet highlight. The specification include the drain source voltage, which is 3 volt, 30 volt, drain current 200 milliampere, total power dissipation to 0.3 watt, threshold voltage between 0.8 volt to 3 volt, on resistance typically 5 ohms, input capacitance is 15 picofarad.
Let's move to part B, number 2, which is N-channel of bipolar junction transistor BJT and field effect transistor FET. So, the purpose is to study and compare the operation of N-channel BJT and N-channel JFET using voltage divider bias circuit. So, let's make simple. For first, N-channel BJT that formed by the combination of two N-type materials and one P-type materials that consists of 3 terminals, which are collector, base, and emitter. Next, N-channel JFET is made of N-type semiconductor materials that consists of also 3 terminals, which are drain, gate, and source. So this is a design of N-channel BJT. We use the formula to find 5 things that are VB, VE, IE, VRC, and also VC. We get VB, IE, VE, VRC, VC, and also VRC. This is our graph of N-channel BJT that we get from the simulation. We use a BJT analyzer from a transfer characteristic graph. This is our design for N-channel JFET. Calculation that we make for find 3 things, which are VG, ID, VGS, and also VDS. So this is our simulation diagram of N-channel JFET. So we can see at this diagram we get VGC, VS, VDS, ID, and also VG. So when we run, we get the graph view of JFET circuit diagram is like this. That is DC transfer characteristic. For first, we want to discuss about the calculation and also simulation result for both N-channel BJT and N-channel JFET. For N-channel BJT, the simulation and also calculation result that we get is almost the exact value, but maybe plus and minus between that value. Meanwhile, for N-channel JFET, we get for calculation and simulation result for VG, RS, ID, VGS, and also VDS. So to conclude, response types for N-channel BJT is current control device. Meanwhile, response types for N-channel JFET is voltage control device. To conclude, from the analysis of the result, it can be concluded that BJT and JFET has distinct characteristics that make them suitable for different applications. BJT that we know that I explained before is for current control device with low input impedance and higher power consumption, making them ideal for high speed and power switching application. Meanwhile, for JFET, suitable for voltage control device with high input dependence and low power consumption. That more suitable for low noise and high impedance signal application. The consistency between calculate and simulate value validate the accuracy of the experimental setup and theoretical understanding. So that's all from us. Thank you. Thanks for watching.